is a squid on tip, which we fabricate by pulling a quartz pipette and then depositing one of these superconductors in 3-step deposition. In the first 2 steps, we make these 2 leads. And in the third deposition step, we form a ring on the edge of the pipette. And as a result, we have a tiny squid, a nanometer squid, that resides on the apex of a sharp pipette. This is how it looks in SEM. This is a lead squid. We can do diameters down to a few tens of nanometers. The flux noise is down to 50 nanophi naught per square root hertz. And the result, we have very good spin noise of a fraction of Bohr magneton per square root hertz. So we incorporate these squids in a scanning squid microscope. And we study various systems, including vortex matter, vortex dynamics that Jonathan and Nahori will be telling later during this workshop, some nanomagnets, magnetism in topologically doped magnetic TIs, topological insulators, magnetism at oxide interfaces, and we can also make more complicated devices with 3 and 4 junctions that have very interesting properties. But today I'll be talking about something different, and this is thermal imaging. So this is a thermal image acquired by an infrared camera, a commercial camera, which shows temperature variations in this landscape. But what is essential physics, interesting physics behind it, is actually dissipation. So the car is hot because we burn gas in the engine. The tires are warm because of friction. Here in our body, we burn sugar. And here we dissipate electrical energy. So in fact, many of the questions, fundamental questions that we ask ourselves in condensed matter physics boil down to dissipation. Questions of decoherence, scattering, loss of quantum information, and so on, are all related to eventually how and where the dissipation occurs. But unfortunately, today we cannot take such an image at low temperatures of a quantum system. And for this reason, we don't actually think in terms of dissipation, because dissipation on a microscopic scale is not a measurable quantity. But what if it would be a measurable quantity? What if we would be able to take such an image of a real quantum system at low temperatures? The wealth of information that we would get would probably cause us to think differently about some of these fundamental questions. So I'll show you some of the first steps in this direction. So coming back to squids on tip, so these are the IV characteristics of our squids using this electrical diagram. The details are less important. What is important is that the IVs are linear up to the critical current, and then they change their characteristics. And the critical current is sensitive to magnetic field. This is what makes these devices sensitive magnetometers. But we all know that the critical current is also temperature dependent. In particular, this is a lead device, so if we go to 7.2 Kelvin, which is TC of lead, the IVs will become completely linear. So if this is such a sensitive magnetometer, maybe it can also be a good thermometer. So let's first see what is available there. So this is a comparison of various thermal imaging techniques in terms of their sensitivity and their spatial resolution of the thermometer. And it ranges from few microns down to 10 nanometers. And the best of them have a sensitivity of about 10 millikelvin per square root hertz. So for example, the infrared that you saw before is somewhere here. And we have Raman, we have fluorescence in nanodiamonds, and so on. So if we take one of our squid devices, 50 nanometers in size, and we measure its IV characteristics as a function of temperature, and then we bias it at some bias current. And then what we have to do is to measure the current through the device as a function of temperature in order to calibrate and to get its thermal response. So the slope here is the thermal response, which in this particular case is about 10 microamp per Kelvin. We have to compare it with the noise, with the current noise of our devices. And it has a 1 over f noise up to a few hundred hertz, and then white noise region on the order of about 8 picoamps per square root hertz. So all we have to do is to divide these numbers in order to get a thermal noise, which comes out about 800 nanokelvin per square root hertz in this particular case. So if we want to compare it to the existing techniques, we have to expand this logarithmic scale, and our device is here. It is 4 orders of magnitude more sensitive than any other existing technique for thermal imaging. In addition, and what is even more important for us, is that all these techniques are essentially room temperature techniques, and they cannot work at low temperatures for fundamental reasons. So infrared, for example, is black body radiation, which goes to 0 at low temperatures. Let's say these thermocouple devices on an AFM tip. It's a Zeebeck coefficient, which goes to 0. Raman and nanodiamonds are all based, their thermal sensitivity comes from essentially measuring thermal expansion, which also goes to 0 at low temperatures, and so on. So now we have a very small and a very sensitive thermometer, but it's not enough in order to do real thermal imaging. There is another important requirement, is that this nanothermometer is well isolated from its support structure. Otherwise, we'll have a very small thermometer which measures actually a bulky thing. In this respect, this device performs extremely well for 2 reasons. First is that the leads to the thermometer, to our squid, are superconducting. So there's no electronic heat conductivity. And second is that the cross-section here is nanometer scale, tens of nanometers. And if you put in numbers, you find out that this is actually the phonon heat conductivity is quantum limited. We have only a couple of channels, of phonon channels to propagate here. And as a result, the thermal resistance between the device and its support structure is extremely high. So effectively, we have a nanothermometer which is completely isolated thermally from all its environment, including our device itself. But we do want to couple it to the device. So for this, we introduce a low pressure of helium exchange gas, which gives us a good thermal link between the surface of the sample and the thermometer. As a result, we have non-invasive nanoscale thermal imaging, which reflects very well the local temperature of the device. So now we can drive, for example, an AC current through this device and to measure the resulting AC temperature. So this is how it looks. This is the AC temperature. As a function of power, since we know exactly what is the resistance and what is the current, so we calculate exactly the power dissipated in the device. And we see that the temperature decreases linearly as expected with the power until we reach noise floor, which in this case about 500 nanokelvin. It's all at 4 Kelvin. All the measurements are done at 4 Kelvin. So actually, we can measure the 6th digit after the decimal point of the temperature. We don't know very well the first 3 digits, but we know very well the last few digits. But what is interesting here is to look at the power. So we go to noise level when the power is few femtowatts. Now, we don't have a good sense of these numbers, so let's take some criterion. For example, Landauer's limit of readout of 1 bit of information. So this is the minimum energy that is required in order to read 1 bit of information, which is kT ln 2, just the entropy that we change in the system. And at 4 Kelvin, it's about 10 to the minus 3, 10 to the minus 23 joules, which is about 8 orders of magnitude less than what we today pay for reading out 1 bit of information in our laptop computer. So it's a small number. But let's assume we have such an ideal qubit, and let's say it operates at a computer rate of 1 gigahertz. So such an ideal qubit would dissipate 40 femtowatts. 40 femtowatts for us is here in this particular device, which is about 100 by 100 nanometers, heated up by 3 microkelvin. So 3 microkelvin is here. This is the size of the device. And of course, the temperature of the device will be inversely proportional to the area, to the cooling power that it has. So this will be this line. which is inversely proportional to the size. So you can think of this line as sort of some thermodynamic line of an ideal qubit that works at 1 gigahertz. This will be the dissipation or the temperature of this qubit, and we are quite well below it. So now we can really start thinking of thermal imaging of real quantum systems. So I'll show you 3 examples. So the first example is quite trivial. We made a nanowire of copper and permalloy. And we applied an in-plane magnetic field along the permalloy and perpendicular. And the first thing we did, we just measured the DC magnetic field. So this is the map of the DC magnetic field. The scale here is in millitesla. And as you can see, the permalloy is fully magnetized. You have high stray field here and some stray field due to the out-of-plane magnetic field. Of course, you don't see the copper because it is not magnetic. Now we can drive a current through this device, an AC current of about, let's say, 10 microamps. This current creates Biot-Savart, and we can measure the Biot-Savart of this current. So this is shown here. This is numerical simulation of this current. And there's no surprises. The current flows along this serpentine, of course, avoiding these protrusions. And this is, now the scale here is in microtesla. But this current also should cause dissipation. So we should see some temperature map. This is how it looks. So this is the temperature distribution of this device in millikelvin. Again, the measurement is done at 4 Kelvin. And what you can see is that we have dissipation in the permalloy nanowires and very little dissipation in the copper. And the simple reason is that the sheet resistance of permalloy is about 100 times larger than the sheet resistance of copper. In addition, you also can see some diffusion along these protrusions where no current flows. This is just heat diffusion through the metal, which is better than heat diffusion in a silicon substrate. So this is a simple example, but the nice feature here is that these 3 pieces of information we measure simultaneously. So at each pixel, we acquire a DC signal, which is the DC magnetic field. We acquire an AC signal at the first harmonic, which is the Biot-Savart, because Biot-Savart is linear in current. And we acquire the second harmonic signal, which is the thermal signal, because dissipation is quadratic in current if the system is linear. So now, I'll show you the second example is a carbon nanotube. So here we have a carbon nanotube that was wound in such a loop. And here's another carbon nanotube that was in this loop. Now we drive an AC current of just few nanoamps. It should dissipate. It should heat up the nanotube. And this is how it looks. So this is the thermal map of this nanotube in presence of a couple of nanoamps of current. The scale here is in microkelvin. And as you can see, the nanotube is heated up along its entire way. However, if you look at this nanotube, the dissipation occurs only here, and you don't see this part of the loop. The reason is that this nanotube was metallic, so it got shorted here, and all the current passes through here, and no current flows in this loop. This nanotube was semiconducting, and therefore there was no short here, and you can see dissipation along the entire length of the nanotube. But if you look closely, you also see some rings, some structure in this thermal image. So now if we zoom on a small part of this device, this is what we see. We see a ring of temperature. The scale here is 50 nanometers. The temperature scale, again, microkelvin. In order to understand it, you have to realize that our device, it is a sensitive magnetometer, it is a sensitive thermometer, but is also a scanning gate. We can apply potential between the squid and the device, and therefore change the local potential in our sample. These carbon nanotubes are highly disordered carbon nanotubes that essentially form a sequence of quantum dots. So what you should think of is the carbon nanotube that we have a quantum dot here. The quantum dot is Coulomb blockaded, so you have current through the quantum dot only when the back gate, or the top gate in this particular case, is at the right position, so there is a conductance through this quantum dot. So essentially, when our tip is in this part, we have, let's say, n electrons in our quantum dot, and it poorly conducts. When our tip is here outside this ring, we have, let's say, n plus 1 electrons, and again, it poorly conducts. But when our tip is exactly along this radius, it brings the quantum dot exactly into the peak of the Coulomb blockade conductance, and therefore there is enhanced dissipation, and we can measure the difference in the temperature of the quantum dot due to change in its occupation by 1 electron. So similar features have been seen in scanning gate microscopy using an atomic force microscope. But here, what is measured is the conductance through this carbon nanotube. Here, instead, we measure the temperature of this quantum dot as a function of the position of our tip. And if we take a cross-section through here, we see that actually the quantum dot heats up by some 50 microkelvin if we put our tip here. And if we move it 20 nanometers away, it cools down by another 50 microkelvin. The last example is graphene. So this is a boron, graphene encapsulated in boron nitride, which we made into this form of a washer. So now we just apply a DC current through this device, and it should dissipate. So this is how the thermal map looks. So we see a sequence of rings all along the edges of the graphene. These rings remind us the rings that we saw in the carbon nanotube, which were quantum dots. So one possibility is that we have sort of quantum dots on the edges. But in order to have dissipation through them, it means that the current has to flow through these quantum dots. So in carbon nanotube, it was a one-dimensional system through which we forced current. But this is a two-dimensional system. So if dissipation is high here, the electrons should just bypass it through the bulk. So either for some reason the current is forced to flow through the edges, which is probably not the case because we're at zero magnetic field here. Or the other possibility, which is what we believe is happening, is that these devices are highly ballistic. The mean free path is larger than the sample size. So we inject ballistic electrons, and the electron-phonon coupling is extremely weak. So the electrons have no way to get rid of their excess energy. So they elastically scatter here all over this device until they hit a specific defect on the edge in this particular case, and that's where they can release their excess energy into phonons, and this is what we detect. So in order to understand it better, I'll show you another device which has a square shape.